Question of KSET 2016, which is based on the concept of Cholesky decomposition. The question says, which of the following matrix admits a Cholesky decomposition? Options are, option 1 says it is a 2x2 matrix, which first row is 1i, second row is i1, and second option says 1, 2i, minus 2i, 1, which is also matrix of order 2, and the third matrix is 1, minus 2, 5, and fourth matrix is 1, 2, and 1, 2. So we have to know when the matrix admits a Cholesky decomposition. We have a result. So we have two cases. A is a matrix, which is a square matrix. A is a square matrix. Here A may be real or A may be complex. We have two cases here. A may be complex matrix. So if all the entries are real numbers, then the matrix is real matrix. If some of the entries or all the entries are complex, that is called complex matrix. Now in case of real matrix, A is a real matrix, then A admits Cholesky decomposition. When A is symmetric and positive definite. Symmetric and positive definite. So symmetric means A transpose is equal to A, which is for symmetric, and positive definite means all the leading principal minors are greater than 0. All the leading principal minors are greater than 0. So this is for positive definiteness. Suppose A is a complex matrix. A is complex. Then A admits Cholesky decomposition only when A theta is equal to A, that is A is Hermitian. A is Hermitian. So A theta is nothing but transposed conjugate of A. Transposed conjugate of A. That means you take the conjugate of each element of A and then take the transpose of that matrix. That will be A theta. So if A theta is equal to A, then the A is Hermitian, and second is A is positive definite. Here also all the principal minors are greater than 0. So whatever the case, if it is real matrix, that should be symmetric and positive definite. If it is complex matrix, then it is Hermitian and positive definite. In those cases, the matrix admits a Cholesky decomposition. Now we will see the options. Here we can observe the entries of the matrix, which is in option 1. We can take it as A. So it is having some complex entries, therefore it is a complex matrix. So for the complex matrix to admit a Cholesky decomposition, first it should be Hermitian. Now consider A, which is 1 I comma 1, which is in option 1. Now for A conjugate, this will be conjugate of each element. Conjugate 1 is 1, conjugate 1 is minus I, conjugate minus I, this is 1. So A transpose conjugate will be, or conjugate transpose will be A theta. This is equal to, take the transpose 1 minus I 1. This is not equal to A. Therefore A is not Hermitian. Not Hermitian means no Cholesky decomposition. This implies no Cholesky decomposition. Now we will see option 2. Option 2 is B is equal to 1, 2i, minus 2i, 1. Now conjugate of B will be taking the conjugate of each element. Conjugate of 1 is 1, conjugate of 2i is minus 2i, conjugate of minus 2i is 2i, because the conjugate of A plus IB is A minus IB. If suppose only A is there, conjugate of A is A only, A plus IB will be A minus IB. Conjugate of 1 will be 1. Now taking the transpose, B conjugate transpose, B transpose, this is 1, 2i, minus 2i, 1. You can observe this is equal to B. Therefore B theta is equal to B. This is Hermitian. B is Hermitian. Now we have to check for all the leading principal minors. The first leading principal is 1 is equal to 1, which is greater than 0. And second principal minor is nothing but advent of B. This is equal to 1, 2i, minus 2i, 1. This will be 1 minus of minus 2i into 2i is equal to 1 plus 4i square is equal to 1 minus 4i. I square is equal to minus 1. This is minus 3. So this is less than 0. Therefore, all the principal leading or the leading principal minus of B are not greater than 0. Therefore, this implies B is not positive definite. So if it is not positive definite, then B has no Cholesky decomposition. Next, we can now see the option 3. So that is C is equal to 1 minus 2 minus 2 1 minus 2 5. Now C transpose will be 1 minus 2 minus 2 5 is equal to C. Therefore, C is symmetric because all the entries are real. Now for positive definiteness, the first leading principal is 1. This is 1. This is greater than 0. Second principal method, determinant of C equal to 1 minus 2 minus 2 5. This is equal to 5 minus 4. This is 1. This is greater than 0. This implies C is positive definite. C is positive definite because C is transsymmetric and positive definite. Therefore, C has Cholesky decomposition. Now we see option 4. So that is D is equal to 1 2 1 2. Now, so here D transpose is equal to 1 1 2 2. This is not equal to D. This implies D is not symmetric. D is not symmetric means, so don't think about positive definiteness. This implies D has, so basic should be symmetric in case of real matrix. D has no Cholesky decomposition. You can observe from the options. A has no Cholesky decomposition and B has no Cholesky decomposition. C has Cholesky decomposition and D has no. So in the given options, the matrix which is given in the option C is having a Cholesky decomposition. Therefore, the correct option is option 3.